Hello, everyone. It is Thursday, the 19th of September, 2024. And before I get into the 9 light experiments, I do want to share some more information about Iran. I did kind of rehash yesterday's video when I realized I didn't really mention the full extent, including the pagers exploding, etc. And but anyway, so Dan Dix from Press for Truth, it was a nice summary, and I like promoting Canadian content.
This is Dan Dix here reporting for Press for Truth with breaking news. Thousands of people are wounded when Hezbollah's new pagers simultaneously explode across Lebanon, killing 8 and sparking mass panic, with sources blaming Israel. Now, for some of my younger viewers who may not know what a pager is, this is technology that was popular 30 years ago, where you could message somebody. They would have this pager in their pocket. It would vibrate or beep. We sometimes call them beepers. And then you would be notified that you have to go and call this person. Now, these were what were used. These are the things that exploded. And there's various reports saying things like thousands of Hezbollah fighters injured in a massive cyber attack, with the Iranian ambassador among some of the victims. But this point right here, the massive cyber attack, is highly contentious, very debated right now, because you got others saying stuff like this. Israel assassinated Hezbollah's chief of staff smack in the middle of Beirut. So Hezbollah realized it could no longer use cell phones, and they switched to pagers. The only problem, they were unknowingly buying explosive pagers from the Mossad. So is this a case of a massive cyber attack, or are these explosives that were, implanted beforehand? Hezbollah doesn't know. They have no idea what just hit them. And in fact, nobody really does at this point. As this article points out, hack attack, beat, boom, 8 dead as Hezbollah terrorists and Iran envoy among thousands hurt after booby-trapped pagers explode in Israel attack. Now, the reason why Israel attack is in brackets is because that's currently unknown at this point, where this is coming from. It's a pretty good educated guess, but it's technically not proven. Same with this idea that they were booby-trapped pagers. The article it goes on to say it right here. It is not clear what caused the pagers to blow, with some experts saying explosives were inside them, and others are saying malware could have caused the batteries to overheat and then erupt. The Wall Street Journal, citing sources, reports that the targeted communications devices in Lebanon were part of a new shipment recently received by Hezbollah. So this would add credibility to the idea that it was, something like C4 planted in these devices and then given to them in this new shipment. But this begs the major question: how could Israel have triggered these Hezbollah pager explosions? Well, either we know it was remotely detonated, and it was clearly either something being planted inside of these devices beforehand, or there was some sort of malware, there was some sort of a hack, and they were actually able to send out this signal to all these particular devices to have them explode. This is still not yet known, and this is exactly what we're going to look into today. In fact, I posted this on Twitter yesterday. Earlier today, I should say, makes one wonder, could something like this ever be in your pocket? Well, folks, we're going to look at all of that and much, much more in this video. But really quickly, guys, before we do, I'd ask that you check me out here at subscribestar.com/pressfortruth. Here you could sign up for a monthly reoccurring contribution. It was a big issue, and so we know this is a real possibility. And as this Zero Hedge article points out, it is yet unclear how precisely Israeli intelligence was able to infiltrate Hezbollah's telecoms, whether this was small bombs that were placed in the pagers themselves, or possibly the result of some kind of large-scale cyber hack. But what is becoming clear is that they were remotely detonated. A Hezbollah official was cited anonymously in Reuters, calling the incident the biggest security breach that the group has ever faced since the start of this nearly year-long conflict with Israel. Groups like Hezbollah often use low-tech devices to communicate with each other, given that cell phones are easier for intelligence services to intercept. So again, we come to this, there's two sides of the story here. There's multiple sources. We still don't know yet what the case is. It could be small bombs that were placed in there, or with potentially much larger implications, it could be the result of some kind of large-scale cyber hack. Now, I want to point you to this next tweet, and I would definitely say take this with a very large grain of salt. This person is not necessarily credible, but this is something that's going out there that I wanted to share with you. The exploding Hezbollah phones was carried out by Mossad. This is technology that I was informed about months ago by people who know Israel tech. Essentially, the Israelis can send a message to a device that instructs it to turn the battery on and off about 1 million times a second, and it causes it to overheat instantly and explode. I was told it can be used against anyone's phone on the earth at this moment. Very Black Mirror. And then this person chimes in and says, nah, traces of highly condensed C4 have already been found. So the guy says, interesting. Yeah, for sure it is. So I chimed in, saying, do you have a source for this information? He says, I was told about this months ago. So I said, no. What's your source that condensed CO4 has already been found? And this person says, Iranian Telegram. So as I said, take this with a grain of salt for what it is, but this is what's going around online. And again, the big question today is whether or not C4 was implanted beforehand, or whether or not this was some sort of hack or cybercrime. What we do know is that it was done remotely, literally at the press of a button, because thousands of these things exploded at the same time. And again, if this was some sort of cyber hack or some sort of crime in that sense, who's to say that this isn't potentially going to happen with every device that has a lithium-ion battery in it? I mean, it's absolutely crazy. But one thing people really need to remember going forward here is that things like cell phones and smartphones, which are now used by over 5 billion people, have already been highly weaponized. They're already Big Brother spying devices. They've already been purposefully made highly addictive. They've manipulated people's thoughts and ideas and opinions through social media. And in fact, as I uncovered in a declassified military document, the radiation and some of the stuff that's coming from this stuff is actually killing mankind. Let's not forget, there are right now 5.6 to 5.7 billion people right now who own and use cell phones. And as I said, I pointed this out years ago. I made this video way back in 2017 titled Wireless Warfare Exposed, Declassified Military Document Proves that Smartphones Are Killing Mankind. We've been treated like guinea pigs, and the lab results are in. Smartphones are killing us. The current number of cell phone users today is 4.7 billion. This was back in 2017, and that number has already grown by 1 billion people, folks. And I say that figure is continuously exponentially going to rise. Decades of cell phone use have now passed, with a new generation of people coming into the world who've not experienced life without these devices. In this video, Dan Dix of Press for Truth goes over what the phone companies are telling you is safe and acceptable levels of exposure, compared to what military documents have reported on as far as back as the 1970s in terms of the clinical effects of microwaves and radio frequency radiation on human beings. Guys, before YouTube terminated my channel, this was one of my most widely viewed and viral videos. It got almost 2 million views very quickly, 1.9 million views. So I want to share this one with you today. If you have not yet seen my video titled Wireless Warfare Exposed, Declassified Military Doc Proves Smartphones Are Killing Mankind, it proves definitively that these things have already been highly weaponized and are being used against us. If you've already seen this video, well, you can stop watching now if you like, but if you haven't, I would strongly encourage you to check it out, because there's a lot of good information that's contained in here that would show you exactly how, yes, it's of grave concern right now that they may potentially have the technology to just at the press of a button, detonate these things. But as you will see, they've already been highly weaponized to be used against society. Exposure. Now we're going to be doing this on an iPhone. This video has one of these either in their pocket or in their hands right now. There's also a really good chance that you are completely unaware of the effects that these devices are having on your psyche and on.
Okay, so that's Dan Dix from several years ago, where he's talking about the effects of the internet, Wi-Fi, phones, phone usage. I think the numbers are a little bit skewed and non-verifiable. And there are, like, is it counting people that have multiple phones, right? Because there are a lot of people that have multiple phones, right? Even phones that they haven't thrown out. So anyway, on with the 9 experiments that will change your view of light and blow your mind. See it. Anyway, I thought I liked it. Maybe it didn't go through.
Are actually 2 different things. Traveling around the universe, delivering energy from one place to another. It helps us see. It provides life to plants, and thus to our planet generally. It has a reputation for being very fast. And yet, for a source of energy that has become synonymous with greater understanding, light is surprisingly difficult to understand. Light helps us see other things better, sure, but when scientists tried to look at light itself, it was surprisingly difficult. No, I don't mean that they started staring into any lamps. Please don't do that at home. But experiments in the last 200 years or so have proven that what light appears to be and what light...
These are blue light blocking glasses, not required for visual aid.
Light is are actually 2 different things. The first experiment on our list highlights the following mystifying fact. Light behaves differently when you're not looking at it compared to when you are. But to understand that, let's begin with the basics. What is light? In the early 1700s, Isaac Newton theorized that light was made up of tiny little particles that he called corpuscles. But in 1801, nearly 100 years later, a man named Thomas Young discovered that light must actually be more wave-like than particle-like. He proved this using an important method known as the double-slit experiment. He set up a source of light and shone it through 2 narrow slits onto a board. Young noticed that rather than getting 2 bands of light on the other side of the slits, a strange striped pattern was
I've shared
forming.
this before.
This was known as an interference pattern and was incontrovertible proof that light had been traveling as a wave. Why? Let's talk about waves for a moment. When waves travel, they oscillate up and down. But when 2 waves try to oscillate the same point in space at the same time, you get something known as interference. Imagine you had a bathtub with a rubber duck sitting on the surface. 2 waves reach the duck at once. One wave tries to raise the duck up. At the exact same time, the other wave tries to drop it down. What happens? Provided the waves are of the same magnitude and are perfectly out of phase, they will cancel each other out, and the duck would not move at all. This is called destructive interference. Similarly, if the waves both tried to raise the duck up at the same time, the duck would be raised twice as high. This is known as constructive interference. Because waves tend to expand in a circle, 2 waves next to each other will start to both constructively and destructively interfere with each other. Here are 2 waves in water. See these lines? These calmer patches are where the waves are cancelling each other out. This is the effect we see with light traveling through the 2 slits. As the light from one slit propagates, it cancels out the other wave of light at certain points, creating the interference pattern that Young noticed on the board. So the mystery was solved. Light was a wave and not a particle. Except there is more to this experiment than meets the eye. Let's fast forward another 100 years to 1905. Scientists around this time had become puzzled by something known as the photoelectric effect. It turned out that when you shone a light on a metal surface, electron-like particles were coming off it. This was deduced to be because electrons in the metal were getting knocked off it by the increased energy the light was imparting. Imagine it like a fruit on a tree. If you pull the fruit off the tree, you need to use a certain amount of energy. Once the energy is greater than the strength of the fruit's connection to the branch, the fruit pops off. This was happening with the light and the electrons. Once the light hit an electron and gave it enough energy to pass the threshold, it broke free from the metal. However, what surprised scientists was that if you increased the intensity of the light, they had expected the electrons to be knocked away faster. If you pulled the fruit off the tree harder, it would come off faster.
Now picture sunlight and how different elements get ionized and behave and react differently based on things like temperature, pressure, and density.
Faster. More energy equals more departing kinetic energy. However, this did not appear to be the case. Instead, increasing the frequency of the light increased the velocity of the departing electrons. The intensity of the light didn't affect the departing electrons' velocity at all, but did affect the quantity of electrons being emitted. It was a bit of a puzzler. Albert Einstein was the man who solved the puzzle. He deduced that light must be traveling in little packets of energy, so sending more of them, increasing the frequency, was the only way to increase the energy going to the electrons. He called these packets photons, and later earned a Nobel Prize for his work. Light, it seemed, was more like a particle again, or both a wave and a particle at once. Of course, even this is not the full picture. To be honest, we aren't completely sure about the full picture even now. Instead, we have more results that are contradictory. Let's go back to the double slit experiment. Armed with the knowledge of photons, physicists once again took a look at the double slit experiment. Experimental techniques had improved in the last 100 years, and it was now possible to emit a single photon of light at a time. So, the double slit experiment was done again. This time, only a single photon would be sent through the slit onto a detector on the far side. When this was done, the detector registered the arrival of the photon at just a single point. So, light was behaving like a particle again. But then, why had it interfered with itself in the previous version of the experiment? Scientists had an idea. They sent through multiple photons, one at a time, and plotted the result on the detector. And this is where the result became really strange. Once again, the detector started seeing the photons arriving at single points, one at a time. But bafflingly, the arriving photons started creating a pattern. It was the interference pattern, the proof that light behaved like a wave. But strangely enough, this was only occurring when a single photon was going through at a time. Somehow, the single photon, which was leaving the detector like a particle and was arriving at its destination as a particle, was apparently in some way traveling through both slits at once, enough to then interfere with itself on the other side like a wave. If light was just a particle, then when it went through the slits, you wouldn't see this pattern. You would only see two blobs of light, one for particles that went through the slit and one for particles that went through the other one. And yet, here was the interference pattern with its multiple lines of light disproving that. Scientists tried to pin light down. They set up the experiment, but this time with two more detectors at the slit, so that scientists could observe whether it was indeed passing through both at the same time. It didn't. But at the same time, it stopped creating an interference pattern on the furthermost detector. And from this, scientists began to realize something. Light cared about being observed. To be clear, It didn't matter whether it was observed by a human eye or a machine. The moment light was
I would like to see like more people duplicate this experiment before looking more into it, and like the mechanism that's being fired off or that's initiating the like the laser or the light. Because if there's like a certain degree of rifling, like there's again, like there's so many factors that can make it where it's linear, and as opposed to like just like center of mass. I hope that makes sense, and has to do with like elevation and angles and things like that. So even if it's off, like even in the slightest, like I'm like less than a millimeter, that would absolutely impact the grouping, right? Especially the vertical. Yeah, to me that's mechanism. If it was like left and right, it would be more, anyway, I won't get into and physics.
interacted with in some way by any particle, which is the only way we can detect light. There's no other way to observe it. It started behaving differently than if it hadn't been detected at all. It was if light was snapping into focus anytime the universe asked it the question of where exactly it was, when without the scrutiny, it appeared to relax into something a little more nebulous. Bizarrely enough, to me, this seems to imply that light actually is more like a wave of probability rather than any discrete particle or wave. Anytime it was asked where it was, it confidently provided a definitive answer. It was at this point on the detector. It was not at.
And when you look at the sun too, I believe it travels in a circular path above us, more localized, smaller than we are being led to believe. But when you map it out, amplitude or time and degrees, distance, measurable, degrees or distance, and then amplitude of the sun's path, it creates a sine wave. And so when you look at a Ferris wheel, like the circular path that it takes, I've shared this before, when you look at it from the side, broad side, you'll see like the circular path that the people on the Ferris wheel take, like in those buckets, whatever you want to call them, rolling around. But if you put it perpendicular to your view, you're going to see essentially like a line, and you're going to see like what looks like the buckets just going up and down on the Ferris wheel instead of doing the circular path. And so perspective is also key.
Any other point, but with no one checking up on it, light seems to be traveling in all directions at once, in accordance with certain probabilities. If you ran the experiment multiple times, you could quantify those probabilities, discovering that it was more likely to be on the bands of the interference pattern and less likely to be in the gaps. But anytime a single photon of light was asked, it gave an answer that was 100% concrete. This is highlighted through something known as the three polarizer paradox. Consider for a moment a pair of polarizing sunglasses. Obviously, these reduce the amount of light that can pass through them, usually by about 50%, depending on the type of lens and the wavelength of light. They work by being formed of thin chains of molecules that run lengthways across the lens. Any light that oscillates in the same orientation as this lens gets absorbed. Any that is perpendicular to the chains can pass through without trouble. The interesting case occurs when a single photon is passed through an orientation that's diagonal to the lens. In this case, you don't get half a photon going through. Apparently, you can't just absorb part of the oscillation that is parallel to the lines and let through the other part that is perpendicular. Instead, the photon snaps into either the one orientation or the other. It either is completely absorbed or passes through entirely, but now with a new perpendicular polarization to match what it would have to have had to have been able to pass through easily. How do we know that the photon wasn't this orientation all along? Because of what happens when you start adding more lenses. When you place a second lens behind the first, you can block out the light entirely, provided the two polarizations are perpendicular to each other. Let's say we rotate the second lens 90 degrees compared to the first one. Any light that gets through the first lens has a 0% chance of getting through the second, like trying to post a letter through a chain-linked fence. As a result, we see only black. But add a third lens, and place it at a 45-degree angle between the other two, and bizarrely, light starts making it through all three lenses again. This may seem counterintuitive. How does adding more blockages increase the amount of light that makes it through? But this result actually rules out the possibility that the light has a fixed orientation. It must be snapping into focus at each new lens, rolling a quantum dice.
They might get into it, but the lens shape as well. If it's a convex versus a concave lens, which gives us off divergent versus convergent light. So divergent light as opposed to divergent light as opposed to convergent light. Convergent light, divergent light.
Each time to see if it was the right orientation all along or not. If it makes it through the first lens, a 50% chance, it only did so because it was oriented perfectly perpendicular to the lens's polarization, which means once it reaches the second, it's coming at it from a polarization that's diagonal. So once again, there's a 50-50 chance that it makes it through. It rolls a quantum dice again, and once again has a 50-50 chance of proceeding. If it gets through this hurdle too, then it again snaps to the new orientation, as if it were that new orientation all along, which it obviously wasn't. Which means that now it's polarized diagonally relative to the third lens, meaning that it now has a final 50% chance of getting through. Of course, some photons do not make it through all three of these probabilistic gauntlets. Only about 12.5% of them make it. But that's more than 0%, which is what was happening previously when you only had two lenses. Light likes to behave in discrete quantities. It is quantum. It seemingly snaps to a discrete value when observed. And honestly, we don't really know why. If you think about a wave, there is no reason why you couldn't simply have half a wave. You could half it again and again an infinite number of times and still have an answer that makes mathematical sense. And yet, it seems that down on a low enough quantum scale, you can't half light past a certain point. You can't have half a photon, or even 1.5 photons. And if you try to do so, the photon instead snaps to one or the other nearest integer based on probabilities, but only when it's asked. Otherwise, it's quite content to exist probabilistically, interfering with itself like a wave as it travels along, before jumping to an answer when later asked exactly where it is. What is going on here? This is still being theorized about. The closest comparison we have to it is something known as harmonics, where on a bounded string, only a certain number of waves can exist. On a guitar string, you can have one wave or two or more, but never a number that isn't a whole number. It seems that light works in the same way. Perhaps something pinches the beginnings and the end of the path light travels down, although what this might be and what mechanisms drive it are unknown as of now. Fundamentally though, perhaps the craziest thing about all of this is that this isn't just about light. Although we focused on light behaving like a wave and behaving probabilistically, all particles of matter do the same. Light is just another form of energy, and energy and matter are linked. Particles of matter, atoms, and even complex molecules have been shown to have wavelengths. Electrons are just as quantifiable and just as driven by probabilities as photons are. We are apparently all driven by probability if you scale things down small enough. So what is everything truly made of? What makes up energy and matter that causes it to behave in the way it does? What is going on under the hood of reality? Why is the universe behaving different when looked at compared to when not? And what does it imply to think that even you are on some level probabilistic? What this all means is anyone's guess. The person who figures it out will be the Einstein of our time. But for now, all we can say is that when it comes to reality, it seems the universe is playing dice. You and the world around you might be a lot less certain than you might have thought. So completes our first few experiments highlighting the strangeness of light. Take a breather for a moment. Give your brain a chance to unknot itself. From here on, it's only getting weirder. If there's one thing I've learned about light, it's that for unthinking energy, light seems to love messing with us. As I just showed you, scientists debated about whether it was a particle or a wave because it keeps exhibiting elements of both, seemingly unable to settle. Bizarrely, it behaves one way when you're looking at it, but a different way when you're not. But at least its speed is consistent. Light travels at the speed of light. No matter your frame of reference, that one thing remains the same. I have some bad news for you. It turns out the constancy of light speed might not be right either, and the next few experiments I'm about to show you proves it. Light might go slower than physics would predict in certain circumstances. And no, I'm not just talking about light slowing down in denser mediums like glass, although that's what I originally intended this video to be about. We have an explanation for that. I'm saying that in some circumstances, light seems to travel a path through time and space that has it either going slower or faster than the speed of light, even if dense mediums aren't present. But the really weird thing is that it ends up at the same destination in space and time anyway. Let me show you what I mean. Light travels at 299,792,458 meters per second. According to relativity, this is the only speed light can travel at, and interestingly, seems to stick to that number regardless of your frame of reference. Two people could be traveling through space, one at 1% the speed of light and the other at 50% the speed of light. But if they both look at the same beam of propagating photons, they will see them traveling at the same speed. Time and distance would seemingly rather warp than allow you to see anything other than light traveling at light speed. Of course, when scientists say this, they are only talking about light traveling in a vacuum. We've known for a long time that as soon as you get matter involved, light gets bogged down and travels slower. Light traveling in air only goes at 299,705,000 meters per second, a full 87,458 meters per second slower than light in a vacuum. Light in water goes around 225 million meters per second. Light going through glass caps out at around 200 million. The reasons for this are intriguing, but fairly well understood, and certainly not physics breaking. When light travels through matter, it's constantly waving electromagnetic fields, gets the electrons within the matter to start moving, like ships bobbing on water. But as electrons moving up and down also generate an electric field that in turn creates a magnetic field, a second light wave is created by these moving particles that crucially overlaps the waves of the original light, albeit one that waves at a slightly different pace to the original light. Exactly what speed varies depending on the material. When two waves meet, they interfere with each other. They take an average, sometimes interfering constructively to build each other up, and sometimes working against each other. So when you take the grand total of all the ups and downs of each wave, you actually end up with a new wave, one that travels at a different speed to the other two, and one that goes slower than the speed of light. Eventually, this propagating wave can reach the edge of the blocking material, and without those electrons interfering anymore, you're left with just the original light again, which is then free to travel along its original path again, at its original speed, as if nothing had ever happened. Scientists have had a lot of fun with this concept over the years. Researcher Lene Howe at Harvard in 1999 was able to slow down light to an astonishing 61 kilometers per hour by sending it through a cloud of sodium atoms that had been cooled to 1 billionth of a degree above absolute zero. 2 years later, Howe managed to slow down light speed to 0 before warming up the cloud and sending it on its way again. You might find that result surprising. However, strange things have happened in the opposite direction too. In 2000, researchers at the NEC Research Institute in Princeton, New Jersey, sent a pulse of light through a cloud of cesium atoms. Alarmingly, when they tried to see how quickly the pulse exited the cloud, it seemed that it exited before it had entered. While this might appear to mess with causality, how can you leave a building before you go inside it after all? Fortunately, there was a simple explanation that saved us from creating too many paradoxes. Although the light pulse traveled faster than light, the light itself did not. This was more an optical illusion than a refutation of Einstein's relativity. Let's take a closer look at a photon of light. As Einstein showed us, each photon represents a tiny packet of waves moving up and down. The speed the waves inside the packet propagate is known as its phase velocity, while the speed at which the packet as a whole is traveling is known as the group velocity. You can also have a wavefront velocity, which is how fast the first photon in a wave of photons can travel. This is a little heavy in its terminology, so let's explain it with an example. Think of a crowd of people doing a Mexican wave. The wave that the people are doing is the phase velocity. You can see the wave traveling along through the crowd. It might look like it's traveling quickly, but the crowd itself isn't going anywhere, so our wave's true speed is 0. These people are the group velocity, or possibly the wavefront velocity. Let's imagine that we wanted to send our crowd marching. They could do so and could keep doing a Mexican wave as they traveled. But although their waving hands might make the wave go really fast in the direction of their travel, it would vanish whenever it reached the front of the crowd. Information exchange couldn't go faster than the walking speed of the crowd itself, regardless of how fast the peaks in the wave seemed to be traveling. Einstein in relativity never claimed that phase velocity couldn't exceed light speed. He just claimed that information couldn't travel faster than light. And if you're trying to deliver a message to someone by sending a crowd of Mexican wavers in their direction, it really doesn't matter how fast they're waving. Until the first person in the crowd arrives, no information can be delivered. Still, this difference between the waves within light and the speed of light itself will become interesting in our next experiment. And this is where things start to get a little weird. Oh, you thought it was weird already? Oh no, this is the really physics-defying part. Let's think back on the double-slit experiment. There, researchers explored how light can sometimes behave like a wave and sometimes like a particle. However, in 2023, researchers from the Imperial College figured out a way to separate the slits of this experiment, not in space, but in time. The way they did this was simple. They took a transparent material called indium tin oxide that, under specific conditions, can be made to be reflective. Indium tin oxide is the stuff they use in most mobile phone screens. They fired a laser at it and then rapidly changed the material from transparent to reflective and then back again. This left only a slim window, a few femtoseconds, where the laser was reflected.
Depends on the medium and the modality, but how it's getting reflected, like the shape of the container, all of this stuff. But light, when it goes through different mediums, again, depending on the shape of it, right, it doesn't curve like people are alleging. It goes straight. And then there's like obviously with light and lasers, even the color of the light matters, and the frequency matters, all that stuff, just to get even like the distance, the range of these lasers and these light experiments.
They called this
sorry for interrupting.
Slit. They recorded what the laser looked like after it had been reflected and found that its frequency had spread out a little bit in the process, But other than that, nothing too crazy had happened. The weird thing was what happened when they sent 2 laser pulses through these time slits in rapid succession. The position of the emitter, the mirror, and the receiver remained the same. The only thing different was the time the lasers went through. Oddly enough, when 2 went through, an interference pattern happened. This was not an interference pattern in the same sense as with the regular 3D space double slit experiment though. This was an interference pattern that had affected the laser's frequency. Certain frequencies of light within the laser faded out, exactly in line with the way intensity faded out in the regular version of the double slit experiment. To visualize why this might be happening, let's draw out this experiment in regards to time. The time slit experiment can be drawn in a similar way to the double slit experiment, except we are going to need to visualize the change in the experiment over time. To do that, let's create a 4D graph where space is along the x-axis and time is along the y-axis. This is easy enough to do. It just looks like this. The photon leaves the emitter to the left, hits the time slit, is reflected, and arrives at the receiver. I've drawn this as a continuous line just to make things simpler later, but the idea works just as well either way. Later, a second photon is released from the emitter. It reflects and arrives at the receiver at a slightly later time, represented in how it takes place higher up, further into the future on our time graph. If light behaved normally, traveling along at the speed it was supposed to go at, this would be the end of it. Instead, light is interfering with itself. This means it must be traveling along a path that takes it through the other slit as well as its own. This is the only way that light could come in with the pattern that we see. And just like in the double slit experiment, it's likely happening on the other side of the slits too. As for why it's frequency and not intensity that's being messed with here, think about the implications of what you might see if light did indeed come in at a different angle like this. Photons come in little packets of waves, as I've previously mentioned. Now, look at what happens if you change the angle at which those waves arrive. Here's how it normally might look. I've added a black timeline here and have highlighted every time the receiver receives a new peak in the wave. Here's what happens when you alter the direction of the wave's arrival. Suddenly, the peaks are coming in much more frequently. The frequency of a wave over time is very much connected to the color we perceive light to be. Lower frequency light is redder in color. Increasing the frequency shifts light's color towards blue. So this color variation makes sense. What makes less sense is what's going on with the paths this light is taking through time. Remember, the straight lines we started with represent the 299,792,458 meters per second that we see light traveling. So what can we say about the photons that are traveling along these paths? For some parts of their journey, they are traveling slower than the speed of light, taking more time to arrive at a destination that's the same distance away. And yet, for other parts of their journey, they are traveling faster than causality ought to allow. From their perspective, they are traveling backwards in time. As a reminder, these 2 emitters on the left are actually the same one, just at different points in time. The same for the receivers on the right. It is a mind-bending result. And yet, according to the results of this experiment performed by a research team at the Imperial College in London, this is what is occurring. The implications of this are startling. Light always travels the path of least time, the route that allows it to arrive at its destination along the path closest to 299,792,458 meters per second, the fastest anything in the universe apparently can go. And yet, it seems to me, in its efforts to locate exactly what path that might involve, light is testing the waters, putting out feelers that check to see if other paths, and seemingly other paths through time itself, might present a more viable solution. These feelers are interfering with photons that travel alongside it, but also with photons that travel a little ahead or behind it in time. To be clear, we never actually detect photons taking any of these other paths. We don't see photons coming in from the future. We never see photons traveling slower than the speed of light, provided there is no supercooling gases providing an explanation for why they slow down. And yet, for interference patterns to occur, to at least some extent, light must be trying out alternative routes through time. Perhaps it's like lightning, testing many different directions to find the optimal path for its destination before finding the one that works and collapsing down that path in one giant boom, all other feelers vanishing and collapsing. Or perhaps some other phenomenon is at play. Who can say? For now, all we know is that light has proved once again that it doesn't play by anyone's rules, at least not rules that we can figure out. Again, now might be a good time to pause and reflect. This experiment we just saw hints that not everything in the physics world goes through time the way we might expect. Light might be playing a little fast and loose with the linear nature of reality. We are comfortable with causality, with the idea of things happening one after the other, and things in the past influencing things in the future, rather than the other way round. This last experiment could be interpreted as throwing a bit of a spanner in that. But sadly for our aching minds, it's not the only experiment to do so. Okay, break time over. Can information travel backwards in time? It's the sort of thing that would be really useful if it were true. You could tell your past self not to eat that burrito that didn't agree with you, or you could reveal to yourself the winning lottery numbers. But it just doesn't happen. The resulting paradoxes alone would make the whole thing laughable. In our universe, time always seems to flow in one direction, forward. The idea of traveling backwards in time, or even simply communicating with your past self, seems so outlandish, it can't possibly be true. So, why is it that on the quantum level, information seems to be doing just this? Alex, stop, you might be saying. You've already shown us that the solid universe around us might be nothing more than probability waves, and that light has some weird element to it that causes it to interfere with other light in its past and its future. But this? Surely it's impossible for information to travel backwards in time. I understand the sentiment. It goes against all intuition, and by all accounts, it doesn't seem possible. In previous videos, I mentioned that objects would require infinite energy to even go fast enough to reach the speed of light. So how could something go so fast as to reverse the usual direction of time and arrive at a destination just not instantly, but before they left? Not even light can do that, and it's the fastest thing we know of. Well, this rule about causality's speed limit seems to mostly apply to the macro scale universe. And by macro scale, I mean everything significantly larger than an atom. But down on the quantum level, time might be obeying different rules, or at least the speed of causality seems to come with some significant caveats. And to demonstrate this idea, we need to look at a man called John Stuart Bell and quantum entangled particles. I should apologize in advance for what I'm about to do to your understanding of causality. Okay, but what are quantum entangled particles? In quantum physics, it's possible to hit two particles together in such a way as to link them together, so that by measuring the one particle, you learn things about the other. For instance, if you know that the particles originally had a total of 0 momentum, and you learn the momentum of one of the newly quantumly tangled particles, you know the momentum of the other particle will be the exact reverse, making sure the total remains 0. Effectively, by measuring the one particle, you can learn things about the other. This works for other particle properties too, such as position, polarization, or spin. On the surface, there's nothing too weird about this. It's no different from me meeting up with a friend and discussing our plans for the evening. We agree to go out, and we agree that I will pay for the evening and my friend won't. Then, no matter how far we go on our night out, or even if at some point separate, I know I will be paying and my friend will know that he won't. This is how Einstein thought it worked, only it turned out that Einstein was wrong. Because as it happens, me and my friend did not discuss in advance who would be paying. And the strangest of all, we still both agree with each other anyway, 100% of the time, no matter how far apart we are. This is the strange thing about quantum entanglement and quantum physics in general. We like to think of particles as having fixed properties. However, our penultimate mind-bending experiment shows that particles only have properties when you detect those properties. Yes, it's like the double-slit experiment again, only that was focusing on a photon's position. It seems that particles are also kind of vague about the whole properties thing, instead only relying on probabilities as defined by a quantum wave equation. This doesn't make sense intuitively. Looking at a thing shouldn't be what gives it properties, right? Well, how would you know? If a tree falls in the woods, does it make a sound? According to quantum physics, not necessarily. Let's talk about the Bell experiment. The maths for this is pretty complicated, but bear with me, it's worth the ride. The experiment was first conceptualized by John Stuart Bell, who wanted to know if particles really did have secret properties that they carried around with them, known as hidden variables, or whether they really were making some of it up on the spot. He noticed an interesting mathematical fact about the spin of particles. Before we go any further, I should probably mention that quantum spin isn't the same as normal spin. Misleadingly, quantum spin actually defines whether a particle is influenced, pushed or pulled, by a magnetic field. The name isn't important, but it is important to note that these particles aren't actually spinning,
magnetic field,
and so can have different spin values in almost any
just like
given.
the radiation belt, or what people for some reason like to call a fucking man's name, but like the Van Allen belt, which exceed like 2,000 degrees Fahrenheit, and apparently upwards of 20,000 degrees Fahrenheit. This is all stuff that I've been researching. I'll get into it after the this video, if you're interested in what I'm looking at.
In direction. Now, let's take two quantum entangled particles, and let's say that we've arranged it so that their spin adds up to a total of 0 between them. This means that if one particle would be pulled by a field, the other will be pushed by it an equal amount along that direction, with the understanding that this doesn't tell you anything about their spin in other directions. One of the features of quantum spin is that if we measure an entangled particle's spin in any given direction, let's say up and down, it will have a 50% chance to be spinning up and an equal 50% chance to be spinning down. But remember, once you measure the other entangled particle, it will have a 100% chance to be spinning in the opposite direction to the first particle. On this fact alone, there is no way to tell if the two particles already knew their spin or are somehow deciding it on the spot and conferring it with each
Look at the background too with what's going on.
other now that they've been asked. But Bell noticed a clever thing by asking a clever question. If you measured two quantum entangled particles from two randomly selected directions, what are the odds that their spin for different directions would match? Now, let's define that at any time a particle is spinning towards a detector, its spin is up, and any time it is spinning away from a detector, its spin is down. What are the odds that both particles would be spinning up, up, or down, down when tested? And what are the odds that they would contrast? Let's formalize this with a little experiment. Here we have two entangled particles with 3 detectors reading their spin in different directions. If particle A and B are both red with the top detector, then one of their spins will be up and the other will be down. They are entangled. This is what we looked at previously. However, if particle A is read using the top detector, while particle B is read with one of the other two, these two directions of spin aren't opposites. So particle B has flexibility in which way it goes. Quantum physics claims the particles are making up their attributes on the spot. So once you'd measured the spin of particle A using the top detector, it was a 50-50 whether the spin on the other particle using one of the other detectors would match or contrast. But this is not what classical physics predicted. Let me show you what I mean. Classical physics claims that particles each carry around secret information defining their spin in any given direction. So, for our 3 tested directions, each particle would have a value already. They aren't making it up on the spot. Let's say, hypothetically, our particle's hidden information states up, up, down for particle A and down, down, up for particle B, as B must be opposite to A for each of the directions 1, 2, and 3. Let's pick out a random detector for A. We select detector 1. Detector 1 tells us that A is spinning up. Now let's select a random detector for particle B. We select 1 there too. This detector gives us a reading of down. 1, 1, up, down. We can actually map out all the possible outcomes of this process of random selection in the graph. There are 9 possible outcomes if you were to only measure from 2 detectors at a given time. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and so on. For each of these possible selections, we have fixed hidden variable results that we know already, because we hypothetically defined them earlier. Let's fill them in now. Of course, if you detect particles using the same detector on both particles, you'll get a contrasting result because they're entangled. But we're not interested in these results. Classical physics and quantum physics both agree on this, so let's remove them. What are the odds that 2 different detectors for particle A and B will see the same result, and what are the odds they'll differ? Remember, quantum physics expected it to be 50-50. Particles are making up their values on the spot, and so it's perfectly random which they'll choose, as they aren't confined by the opposites rule here. But in this table, classical physics says that contrasting results only happen a third of the time. The other times, they're either both up or both down. If we do this many times, assigning different directions each time, and ignore exceptions, for instance, where the spins of the particles are all up, 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 or down, 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 once you crunch the numbers, the important thing to take from all of this is that according to the maths, classical physics predicts a matching outcome 55% of the time, while quantum physics continues to simply predict 50%. Pretty table be damned. This percentage difference was the key. By quantumly entangling particles and running this test over and over again, you could now see which percentage was correct. And it turned out the winner was quantum physics. Particles were just apparently making up their spin results on the spot, which is spooky. Because not only does that call into question our perceptions of reality itself, but that also means that the moment one particle decided on its spin result, its quantum entangled partner instantly knew that that decision had happened. You could test both particles at once, no matter the distance, and this same result would come back. Somehow, information had traveled from the one particle to the other in no time at all, far faster than light
It kind
itself.
of reminds me of a school of fish, like little fish, right? Like when they travel in schools, whatever you want to call it. And if one's even alerted by threat, then like the whole like school of fish like can like on a dime like just move in a complete different direction, up, down, left, right, whatever. Yeah,
Elf.
based on things like frequency, waves, vibration.
So already something strange was going on here. This result disproved Einstein's predictions and showed that some information does seem to go faster than light. But we can take this one step further and have information going back in time. There is another experiment, our last experiment, known as the delayed choice test. Its primary purpose was to explore the fundamental nature of light, whether it was a wave or a particle, and to figure out when it decided to be one or the other. Unlike the double slit experiment, though, this test was more about that last part, trying to identify the moment the waveform collapsed down into something discrete. In the double slit experiment, light seemed to choose a different path through space depending on whether it was observed or if it wasn't. In 2006, a number of scientists asked an interesting question. What would happen if you tried to observe the light after it had to pick a path? Consider this experiment. A single photon is sent into a beam splitter with a 50-50 chance of either being allowed to carry on its way along path 1 or getting reflected up along path 2. Once on either path, the photon is bounced off mirrors, with both paths reconverging here, where the other beam splitter is inserted. Once again, the photon has a 50-50 chance to go either way, with an even chance of arriving at one of the two detectors. If light were just a particle, sending a single photon into this experiment would give you an even chance of it arriving at one detector or the other. You'd not be able to tell which way it went, as the two beam splitters make that impossible to know. But you could see where it ended up. However, this does not occur. When the second beam splitter is present, the light produces an interference pattern, indicating that the single photon went down both paths, ultimately bumping into itself before moving on to both detectors. This seems like strong evidence that light is a wave. It certainly behaves like one here. But what happens if you remove the second beam splitter? Suddenly, you know which path the light traveled down. If light arrives at the top detector, it must have arrived from path 1. If it arrives at the side detector, it must have come along path 2. And something about this knowledge spooks the light. It stops going down both paths, and suddenly, each photon only arrives at one detector. Here's the question. What happens if you insert the beam splitter after the photon has already started down either one or both routes? This is why the test is called delayed choice. If you delay choosing how exactly you intend to detect the photon, whether by knowing which path it came down or making that ambiguous to you, what happens to the light? What happens is a very strange thing. When this experiment was performed, it was done multiple times, with the beam splitter randomly being inserted or not, but always being inserted after the photon had entered one or both paths. And yet, the results came back unequivocal. If the beam splitter was present, the photon suddenly and seemingly retroactively stopped picking a path. If the beam splitter was removed, the photon seemingly knew it would later be detected and picked a specific path to accommodate. Somehow, the beam splitter being added or removed in the future changed what the photon did in the past. So, what is happening here? Is it really true that particles somehow saw the future? Did the experiment cause information to be sent back into the past? Or is there some other principle at play here that explains this whole thing, that accounts for the instant transmission of information between quantum particles, and allows it to be perfectly rational that light could travel down one path or both at the same time? Personally, I'm inclined to think that this is more likely. We clearly don't understand what is happening here, but it must be admitted, if we don't understand what is happening, there's nothing to say that causality isn't being ignored. In some way, maybe on the quantum level, time really is more fluid than it is up here in the larger universe. Maybe space and time simply do not apply down there. And maybe one day, someone will be able to come up with a theory that allows all these strange phenomena to finally make some sense. Until then, We'll just have to keep asking the same question. Can information travel backwards in time? Until then, we'll just have to all agree on one thing. Quantum physics is strange.
Yeah, I really enjoyed that video. I hope you did as well. And so I'll just, I'll share some stuff that I was looking at because of Colonel McGregor going on Redacted the other day. He had mentioned 13,000 mile per hour test flights and stuff like that. And anyway, so I got interested in that because I'm like, oh, that's interesting, since the diameter of the Earth is approximately, allegedly, I don't believe this to be true, but 7,917.5 miles in diameter. Anyway, so almost double. So anyway, so it would take like half an hour for this test flight to travel the diameter of the Earth, the alleged. So this is from 2012. This is what the research got me. This was from LA Times by W.J. Hennigan. The results are in from last summer's attempt to test new technology that would provide the Pentagon with a lightning-fast vehicle capable of delivering a military strike anywhere in the world in less than an hour. And then it talks about friggin' DARPA. Interesting. Defense Advanced Research Projects. The Arrowhead-shaped unmanned aircraft dubbed Falcon Hypersonic Technology Vehicle 2 blasted off from Vandenberg Air Force Base northwest of Santa Barbara into the upper reaches of the Earth's atmosphere aboard an 8-story Minotaur 4 rocket made by Orbital Science Corps. After reaching an undisclosed altitude, interesting. Anyways, the aircraft jettisoned, so dropped from its protective cover atop the rocket, then nosedived back toward Earth, leveled out and glided above the Pacific at 20 times the speed of sound, or Mach 20. The plan was for the Falcon to speed westward for about 30 minutes before plunging into the ocean near Kwajalein Atoll. I'm sorry for mispronouncing that. About 4,000 miles from Vandenberg. But it was ended about 9 minutes into flight for unknown reasons. The launch had received worldwide attention and much fanfare, but officials didn't provide much information on why the launch failed. On Friday, DARPA said in a statement that the searing high speeds caused portions of the Falcon's skin to peel from aerostructure. The resulting gaps created strong shock waves around the vehicle as it traveled nearly 13,000 miles per hour, causing it to roll abruptly. This was interesting. The Falcon, which is built by Lockheed Martin Corps, is made of durable carbon composite material, which was expected to keep the aircraft's crucial internal electronics and avionics only a few inches away from the surface, safe from the fiery hypersonic flight. Surface temperatures on the Falcon were expected to reach more than 3,500 degrees, hot enough to melt steel. Yeah. So anyways, there's more in this. This was 12 years ago. So I'm just going to close that down, because then it just got me on other tangents. So what metals are used in spaceships and why? Talk about aluminum, and aluminum composite materials are used on spacecraft. But again, anyway, like I could share what just check out when what temperatures aluminum melts at, and aluminum alloys. But anyway, composite materials are used in spacecraft. Aluminum is light but also very sturdy. Using titanium alloys can also strengthen the body of the ship. So then it said the space shuttle also had very special thermal protection tiles, which helped it survive the heat re-entry. They are made a ceramic composite, which with the bottom of the tiles made from a carbon composite to provide for the heat protection. Okay, so I'm going to shut that down. Then it got me on other tangents. Okay, so this is from nasa.gov history, STS-1 pages, TPS, HTML. The Shuttle Thermal Protection System, TPS, by Dennis R. Jenkins. And so, yeah, I read this. During the original studies of lifting reentry vehicles during the late 1950s and 60s, there had been a great debate over the relative merits of active cooling systems versus passive systems for the vehicle structure. The active systems were attractive on paper, but nobody could quite figure out how to make them work. Anyways, talks about all this stuff. Things began to change as the Lockheed missiles, so again, Lockheed Martin connected to this, as mentioned, and space company made quick progress with the development of ceramic reusable surface insulation. So that's what they're talking about. And this work began in the late 1950s, and by December 1960, Lockheed had applied for a patent for a reusable insulation material made of ceramic fibers. It goes into descriptions, but the Apollo design changed, and the radome never flew. However, the experience led to the development of a fibrous mat that had controlled porosity and microstructure called Lockheat. The mat was impregnated with organic fillers such as methacrylate, plexiglass to achieve a structural quality. Interesting. But if you look at the degrees, 2,500 degrees Fahrenheit, a test sample was flown on the Air Force Pacemaker re-entry test vehicle during 1968, reaching 2,500 degrees Fahrenheit. And so yeah, that's the temperature can withstand 2,300 degrees Fahrenheit. While white tiles protected up to 1,200 degrees Fahrenheit, flexible reusable surface insulation FRSI protected areas not expected to exceed 750 degrees Fahrenheit. Interestingly, NASA and Rockwell originally believed that the leeward side top of the vehicle would not require any thermal protection, but in March 1975, the Air Force Flight Dynamics Laboratory conducted a briefing for space shuttle engineers on the classified results of the Asset Prime and Boost Glide reentry vehicle. And because the leeward side heating was a serious consideration, the thermal environment was not particularly severe, but it easily exceeded the 350 degree Fahrenheit capability of the aluminum skin. Guys and girls, FRSI blankets were subsequently baseline for this area. So again, aluminum skin, 350 degrees Fahrenheit. So I'll just close that down. And anyway, two Van Allen belts. But what temperature is a Van Allen belt? So it ranges from 2,000 to 20,000 Kelvin. And you're not going to get a lot of good information on here. 35,000 degrees Celsius at its highest temperatures. Like, come on, guys. Like the within the magnetosphere, with really, really, really high heat signatures, whatever you want to call it. Yeah. So I was looking at that. I'll still dig into it. I also talked about carbon. The melting point of low carbon steel is 1,410 degrees Celsius, 2,570 degrees Fahrenheit. This type is further classified into medium carbon steel, high carbon steel, and ultra high carbon steel, with melting temperatures ranging from 1,425 to 15,040 degrees Celsius, or 2,600 to 2,800 degrees Fahrenheit. So anyway, which is another reason why I believe that this is a contained environment, because of the Van Allen belts, or the radiation belt, the whatever you want to call it, hyperboloids and toroidal fields that make up the container. And this is just to verify what you get when you search Google. The diameter of the Earth is 7,917.5 miles, allegedly. Again, I don't believe that. Anyway, there's more I can talk about, but I won't. So on that note, I will leave it at that. And I hope that everyone has a wonderful rest of your day.